14.3 partial derivatives. This is the first video for problem set 7 where we cover partial derivatives. Second video we'll talk about differentials and linearization. So what's meant by a partial derivative? Well, suppose we have a function f of xy is equal to 2x to the fifth y to the seventh. This funny 2 without a tail on it is called a partial derivative of f with respect to x, and which we use in a multivariable situation. If there was no y here, we just call it df dx, but we have a y, so it's assumed here that y is constant. If we had 3 variables, then we'd be holding 2 variables constant. So the partial of f with respect to x, 2 and y seventh is a constant. So we really have 2 times 5x to the fourth y to the seventh. The 2 and the y to the seventh are constant multiples, so those get carried along for the ride. We just differentiate the power of x, and of course we can simplify that as 10x to the fourth y to the seventh. In a similar fashion, partial of f with respect to y, the 2x to the fifth is constant. So we have 2x to the fifth times 7y to the sixth. And of course 2 times 7 is 14, x to the fifth, y to the sixth. Now of course we have second derivatives. If we do second partial of f with respect to x squared, this is Leibniz notation, not the best notation. Nothing actually gets squared. Really what this means is partial with respect to x of partial of f with respect to x. It's a partial of a partial, and if you collect all the symbols together, we have 2 partial symbols. That's where the square comes from. And partial x, that's where the second square comes from. Nothing gets squared dimensionally speaking. It's just a derivative of a derivative. And so if we're going to take an x derivative of this and multiply 4 times 10x to the third, 40x to the third, y to the seventh is constant. And similarly, partial squared f with respect to y squared. Y partial of this, we're going to multiply 6 times 14, make that a fifth power. 6 times 14, 84x to the fifth, y to the fifth. The x to the fifth stays because it's a constant. We can have mixed partial derivatives. Partial squared f with respect to x with respect to y really means partial with respect to x, partial of f with respect to y. And so in this case, we do the y first, do the x second. Order sometimes can be important, but not always. We'll see in a minute. So we have to go over here and grab the y partial and do an x partial of that. So we have to do an x partial is 5 times 14 x to the fourth. And so we got 70 x to the fourth, y to the sixth. Now you can switch the order, partial squared f with respect to y with respect to x. That means y partial of x already taken. Need a y partial of this, and what are we going to do? 7 times 10 is 70 x to the fourth, y to the sixth. Surprise, surprise, that is the same as that. And there's a theorem that's pretty basic. These are equal provided these derivatives are all exist and are continuous. It's a pretty simple theorem, and that's true for pretty much everything you can conceive of that you can differentiate. if you look at it, if you take a function like f of x, y, let's look at another one, equals 10x to the third, y to the fourth, and we're finding the two partial derivatives, partial squared f with respect to x with respect to y. If you think about it, the y partial we multiply by 4, the x partial we multiply by 3. Now if we do it the other way around, this says the x partial you multiply by 3, the y partial you multiply by 4. 3 times 4 is 4 times 3, they're both 12. And in both cases, we subtract 1, subtract 1. You can predict what the answer is. Guess what? 12 times 10, 120, x squared, y to the third. And 120, x squared, y to the third. It makes perfectly good sense for polynomials, but it's true for virtually every other function as well. Here's another function. Let's see if we can look at, for instance, sine x squared y. Partial of f with respect to x, if your derivative rules are rusty. Well, the derivative of sine is cosine x squared y times the partial with respect of x squared y. And we do that by the chain rule. And so in this case, we get cosine x squared y. Now an x partial is just 2xy, easy peasy. And let's look at a few more derivatives. This is a good review of all the basic rules from Calculus 1. And let's suppose f of x, y equals sine x squared y. And we want partial of f with respect to y. Well, that's simply going to be cosine x squared y times partial with respect to y of x squared y. And normally you don't have to write this as a separate step, but I'm just showing you what I'm thinking. X squared y. Now the y partial, this is just a constant times y, so that's just x squared. So we have a couple of derivatives here. Let me just write this down here for future reference. We have partial of f with respect to x is equal to 2xy cosine x squared y. Partial of f with respect to y. You can put the x squared in front, not essential, but we'll do it. Cosine x squared y. Now there's two first partial derivatives. Let's find partial squared f with respect to y with respect to x. And that means we have to do a y partial of this derivative right here. You do x, then y. Although we saw before it wouldn't matter. It wouldn't matter in this case, but we'll just show it in the case of a cosine. Now, since we need a y partial, we're going to think of this as two functions. And we have a product of these two functions, so we're going to use the famous rule called the product rule. We can take first times the y partial of the second. You've got to keep in mind what derivative we're taking here. The y partial of this is negative sine x squared y times the y partial of this is x squared plus derivative of the first, it's a y partial of the first, which is 2x, times the second one left alone. Okay, and of course you can simplify this. You can pull the negative out and you can combine that. It's 9th grade algebra, I'll let you do that. Now, let's do partial squared f with respect to y then x. So we need to take this derivative and take an x partial of that result. And sure enough, we need a product rule because we have function of x, function of x. So we're going to think of this as a product of these two functions. So you can take the first derivative of the second, negative sine x squared y. Keep in mind we're doing an x derivative. The derivative of this is 2xy, plus the derivative of the first times the second. And if you look, these terms match up. That's the same here. This is the same as this. The x and y's are shuffled around a little bit. You have 2xy, 2xy, and x squared, and a negative, and a negative. It's the same thing. So that certainly checks. Now, one more derivative, and then we'll move on to a couple more examples and some notation. Let's suppose, for instance, this one right here, we want to do partial squared f with respect to y squared. And we need a y partial of this. Well, this x squared is a constant, so we don't need the product rule. You can use the product rule, but when it comes to taking the derivative of that, it would be 0. So it's kind of a phony application of the product rule. So all we need to do is treat that as a constant times a cosine. Now the y partial is going to be x squared times negative sine x squared y. Now we need a y partial of x squared y, which is just x squared. That's a constant times y. And of course we can simplify that to negative x to the fourth sine x squared y. Okay. Let's look at a couple exponential functions. Again, we'll need the chain rule. Let's suppose we had f of x, y equals e to the 2xy squared. A new notation, instead of partial of f with respect to x, we're just going to say f subscript x. It's less writing. I'm not sure who developed this. F of x notation was Euler. He came a couple of generations after Leibniz, born in 1708, died, or 1706, I forget, died 1783. By then, most of Leibniz's important work was done. We're going to do partial of f with respect to x. Well, e to the 2xy squared times partial with respect to x, 2xy squared. Okay? The e is unaltered here. And so, and again, this part right here is by the chain rule. And so we have e to the 2xy squared, x partial of that. If you write this out, one nice thing about writing this out is it's easy to keep track of what the derivative is. When you're doing mixed partials, sometimes you forget whether you're doing x or y. So do an x partial of that. That's constant. That's a variable. It's just 2y squared. Now, if we do partial squared f with respect to x squared, we need another x derivative. That's a constant, so we don't really need the product rule because we're doing an x derivative, which in this case we can call this f subscript xx. And so you can pull this constant out front, 2y squared e to the 2xy squared times partial with respect to x, 2xy squared. And guess what? We end up with another 2y squared. And so that's going to be 4y to the fourth e to the 2xy squared. Okay. And just another further comment. f sub xy, the way the subscript notation reads is that's first, and that's second. We read from left to right. Okay, that's the process indicated by f sub xy. Now, of course, as we saw before, most of the time these are equal, so you could reverse the order, and although you'd have a different process, you'd have the correct result. So let's do a y partial of this. Y partial of fx, we already did x, we have to do y. And if you look at that, that's what we have to differentiate. Now we are going to need a product rule because we have function of y, function of y. So we're going to do first e to the 2x y squared times the derivative of the second, which is 4y, plus a derivative of the first, which is e to the 2xy squared times 4xy times the second one left alone. Okay, the y partial of that's just 4xy. And that's how we do that. So you're certainly welcome to do any simplification. Sometimes it's easier to do one than the other. Suppose you have f of xy equals 2x squared y plus arctangent of y, for instance, and we want to find f sub yx. Well, why do the y first? Because this is going to give us a function of y, and the x derivative is just going to be constant. So why not do this order? You can switch these orders in any way you want. So we're going to do an x partial first. Okay, we do an x partial here. We get 4xy. That's a constant term, so we get plus 0. Now then f sub xy, we need a y partial of this, so we simply get 4x, and we make quick work of that. So that's our basic lecture on partial derivatives. We'll be back with a lecture on differentials and linearization.